Alright, so on this video we're going to look at doing instance segmentation and object detection within ArcGIS Pro using the mask RCNN algorithm or method. So before we get into the methods, I just wanted to discuss the data and the problem. So here I'm replicating this study. So the goal of this study was to try to extract geomorphic or landform features associated with surface mining. And specifically what we're looking at here are these features known as valley fill faces. So now let's zoom down here to a picture of the features. Okay, so these are what we're looking for. These features are prominent in southern West Virginia, eastern Kentucky, southwestern Virginia, in the mountaintop mining region. Effectively what happens here is the mountaintops are flattened to remove thin coal seams, and there's a bunch of overburden rock material left over, and it's too complicated to move that far off site, and the slopes are too steep to recontour to the original contour. So they have a lot of overburden material and have to do something with it. So what they end up doing is placing a lot of it in adjacent valleys, then creating these terraced filled valleys. So effectively, valley fills are just a geomorphic feature resulting from mountaintop mining and then subsequent reclamation. And as you see here, they have a fairly prominent distinctive characteristics with these like triangle shapes and then terracing. One thing to note, I'm calling these valley fill faces as opposed to valley fills because the actual extent of the fill is gonna generally extend out into the mine complex. And it's really hard to tell where the fill ends unless you have like a pre and post DEM to difference them or something. But the faces of them are fairly prominent, so we're just looking at the faces. Okay, so in this study, we looked at using mask RCNN, which is an instance segmentation deep learning method, to try to extract these features from topographic data. All right, so let me show you what this data looks like. So this is the data that we use to train the model. This is kind of an odd extent. It was selected based on the abundance of valley fills and then also where there was LiDAR data available. I'm just going to zoom into an area here so you can see some valley fill features. So as you can see, these are fairly prominent. Then there's a good bit of them on the landscape here. This surface that we're looking at is known as a slope shade. This is an alternative to creating a hillshade image. And basically the idea is that you create a slope surface and then you invert the collar ramp. So the dark shades indicate steep slopes and the bright shades indicates flat or shallow slopes. And then I convert that into a 0 to 255 or an 8-bit data set. So as you can see here, it creates a very detailed representation of the landscape. This data specifically is a resolution of 2 by 2 meters. It would actually support 1 by 1 meter. It was just coarsened for this specific study here. Okay, so that's the input data. So if you want to actually get a hold of this data, we've made that available on our website. So if you go to the West Virginia View website and then under Research, you can download this data set here, so vfills DL. So once it's downloaded, it'll be a compressed file, and then you're going to need to uncompress it before you can use it. So let me show you what that folder looks like once it's uncompressed. So once it's uncompressed, you get these subfolders. So we have a training area, we have a validation area, and then a testing area in West Virginia. And then to test model transferability or generalization, we have 3 other data sets, one in Virginia, one in Kentucky, and the second one in Kentucky. Excuse me. So if you let me pull this paper up here. So basically the model in the paper was trained on this blue area, and then it was validated in the green area here, and then we had a test set here in the orange area, and then we had these other areas, these 2 in Kentucky and this one in Virginia. We also looked at some other DEM inputs. That's what these dash patterns represent, and we're not dealing with that here. Okay, so as you can see, these features are fairly prominent. So in the training set, we had a total of 1,105 valley fill features to train on. Then the test set had 118, and then the validation was 182, and then in these other areas we had 540, 149, 153. So anyway, there's lots of features. So I think this was a good problem, and it's kind of unique because instead of looking at just images, we're trying to do an extraction using some other type of data, in this case, digital terrain data. Okay, so I think that's pretty much all you need to know to get started here. So if you want to get some background on MaskRCNN, we cover that to some degree in the lecture, our deep learning modules. ArcGIS also has a really good page on how this process works. The key thing here is that this is an instance segmentation method. So it's not, in contrast to semantic segmentation, is actually going to take each unique instance of a feature and note that it's a unique instance. So instead of just getting like building and not building, in this case, as in a semantic segmentation, you actually get each individual building differentiated. So each instance of the building class. MaskRCNN is capable of generating pixel level instance mask and also bounding boxes for each instance. And we'll look at both of those here. Okay, so I think that's all the background. So we can jump into this and start setting up our experiment. So now I'm not going to recreate the paper. The original paper was done using code and mainly using Keras. So I just kind of want to step through a process of how you would get output from beginning to end, just kind of based off the paper, but it's not the same experiment. Okay, so I pulled in some of the data layers here. So these are our train valley fills and the training extent, and then I have a mask that masks the extent there for the training area. If we open up this attribute table, you can see that there's a total 1,105, as I mentioned earlier, and they're all the same class. So I have this code field that just has 1 in it, so all features are coded to 1. Okay, and then later on we'll look at some data for Kentucky just to see how it does, how the model translates over to another data set. Okay, so with MaskRCNN and ArcGIS Pro, it seems to work best if you give it a 3-band image. And this is actually just a single band raster. So in order to get around that issue, I just took this image and I created a composite where each band is effectively the same data. It's not very memory efficient. There's obviously some redundancies, but it seemed to work better for me that way than trying to feed it in just a single band grayscale image. So I bring in the original slope shade image, and then I use the Composite Bands tool. Let's have a look for that. And toolboxes, Composite Bands. It's under data management here. So basically you can just give it that same data set 3 times and then write it out, and you basically get a 3-band image where the slope shade is each channel. Now what you could do is you could experiment with creating other variables, like other terrain variables, and use those as the subsequent channel. So like a topographic position or topographic roughness or surface curvature or something. But you'd have to create those. Note that the data set that we provided, it provides the hill shade and then also the DEM, or original DEM, if you want to create other variables from it. Okay, so once you run the Composite Bands tool, I end up with this. So this is the slope shade as a 3-band data set. It's just replicating the layers in all bands. If we look under source here, we can see that. So it's 3 channels, 2 by 2 meter resolution. It's a TIFF file, and specifically it's an 8-bit. Generally, I find that these deep learning models work best if you're feeding it 8-bit data. It's as opposed to float or 16-bit or something. Okay, so now we basically have a raster, which is what we're going to predict on top of. We have some training samples as vector polygons, all these little valley fills, and then we have a mask extent. So the next step is to actually create some training data from this raw input data. So we can do that with the export training data for a deep learning tool. Okay, so to run this tool on this data, we're going to, first you want to feed it the slope shade here. So I have 2 in here because I pulled in the Kentucky one for later. There's no additional rasters. You're going to point it to a folder where you want to store your output. It's generally best if this is a empty folder. I'm just going to do that here. We'll just create a new one real quick. So I'm just call this, let's see, chips train 2. And okay. And then it's going to give you a little warning there. It's just basically saying that the folder already exists, which is fine because we just created it. Then we want to feed it our training samples. The class value field, I generally found that this works best if it's defined as a long or short integer, and you want to have a unique code for each class. This is really only one class, so they're all just coded with 1. You generally want to not start with 0 because it'll get reserved for like background. So 1, 2, 3, right, if you have 3 categories. All right, and then we want to have a mask feature here, so we're going to do train mask. And I'm going to export to PNG format. And then you could fiddle around with changing the size. Remember that MaskRCNN is a fairly complex model. So you probably are going to want to not use a giant size. I've had this work before with 512 by 512. I haven't tried anything larger than that. So here I'm going to leave it 256 by 256. Note the stride is set at 128 by 128, which means that the chips are going to overlap by half in the up and down directions. If you didn't want them to overlap at all, then you could just change this to 256 by 256 there, and then they'll be butted up against each other, no overlap. We don't need a rotation. We can leave it at map space. One thing I did for this experiment, which makes it take a lot longer to create the chips and to train the model, but I thought it was useful, is I selected output no feature tiles. And the reason why I did that was because there's lots of complexity in this landscape, so I wanted the model to see a lot of different representations of the background or not valley fill terrain characteristics. And then this is important for MaskRCNN. We need the format here to be set to our CNN masks. Okay, and then that's set up, and then if you hit run, it'll generate those chips. For me, this took a while. Let's just go into my history here. I believe it was this one. Let me see here. Oh, sorry, let me see if it tells me how long it took to... It took 5 hours and 40 minutes, roughly 6 hours to generate all these chips on my machine. So anyway, we're not running that now, obviously, but if you do try to replicate this, it will take a while to generate all these chips. If you want to try to run the model without all the background chips, that will speed it up pretty significantly. Okay, so once we run that, let's see what it actually generates. So I'm going to go into the Valley Fill, or my Valley Fill data folder here, and I wrote those original chips in this chips train folder. And as you see here, you end up with a couple different output. The model you can ignore for now. That has to do with the training process. What it generates from the export training data tool is the images. And you see we have a bunch of PNG files here with ancillary data. So there are a bunch of 256 by 256 image chips. And they're all the images with no overlap because of the stride that I set. But it also has... but it's all the chips, not just the ones with the valley fills in them. And then we have labels, and these are for class 1. Only the chips that had valley fills had labels generated. Note that these show up as black because these PNGs, it treats them like a 0 to 255 8-bit image, so it's really 0 and 1, so it's just drawing everything as black. If you're concerned about that, you can always open one of these up in your in Arc and do like a unique value symbology to see the output there. Let's see if we can do that real quick without it taking forever. So I'm going to into that chips folder here. So train chips, images, nope, labels, 1, and we'll just grab this first one here. It's tiny, so we don't really need to give it pyramids. Let's zoom in. It's still trying to draw it, I think. There we go. Now zoom in here. You can see the feature there. We turn that off. So there's our 0 to 1 mask. And let's, well, we don't need to pull in the chip. We can just look at the underlying image here. But you can see there that feature that was drawn in. So that's effectively what we end up with. And if you have chips that have more than one valley fill in it, they're not all going to be coded as one. They're going to get coded out from 1 to however many features are in that chip. So that's the difference between semantic segmentation and instance segmentation, where you need to differentiate the instances, not just the classes. That's why, so if there were multiple classes, you would get a different folder for each class. And then inside of that, all the chips are going to have 1 through the number of samples labeled in each chip. Okay, and then some ancillary data gets spit out here. So there's this map file, and that shows you how the images map to the labels. Note that only the ones that have a that had valley fills in them actually have a label. The rest are just blank, so it'll just have like a zeros mask. And then this stats object here tells you a little bit about the data. So this generated 33,720 chips, which is a pretty decent data set. There's 3 channels because we replicated the slope shade 3 times, and then 256 by 256. There was a total of 2,762 features, and that's more than the total number. That's because some features were split across different chips and they were duplicated. There was the maximum number of features or instances in a single chip was 6. The minimum was 1 because it only exported ones that had at least 1 feature, or made masks for ones that had 1 feature, and the mean was 1.18. So most of them had 1, but some had more. Yeah, there you go. And then it tells you a little bit about the size of the features and whatnot there. Okay, so it looks like we got a training data set. Okay, so now what we're going to do is look at how we can train the model once we actually have that. So all the deep learning tools and whatnot are inside the image analyst tools here, and then they're under deep learning. And what we want to do is train deep learning model. Okay. All right. So the first thing it's going to have you do is give it some training data. So, sorry, I'm in the wrong folder here. So you want to basically give it the folder that has all your chips in it. Where are we? And valley fill data. Okay, there we go. So it was this chips train. And then you can give it a model output. We'll worry about that in a minute. Let's go down here and look at some of the model parameters. So based on the type of training data, it should automatically select a model that works. So see, it only really lets me use mask RCNN here because of the type of data that was generated. Different types of output data or training samples, you might get more options here. The batch size is set at 4. I ended up leaving that, and it worked fine for me. It depends on your hardware, your GPU. I have a RTX 2080 graphics card in this, and it worked fine. I think it's got 11 gigs of memory, but you may need to decrease that. You could try to increase it and see if it works without running out of memory. The chip size was set at 224, but we use 256, so I'm going to set that up to 256. I didn't set a learning rate. If you don't set a learning rate, it'll go through and try to select a learning rate, and I generally find that works pretty well. There's a bunch of backbones available here, all the different ResNets. So the default is ResNet 50. Note the higher you set this, the more layers there are that need to be trained, and the larger the model is going to be, it'll be slower to train. You may run out of memory or have to throw in smaller batches. On my machine, I tried ResNet 50 and it worked, so I'll just leave it at that. If you had a pre-trained model that you wanted to initiate the weights on, you could add that in there. You can set a validation percentage, then that's what's going to be withheld to validate the model at the end of each training epoch. And you could change that. I'm just going to set it up to 20%. Since I'll be honest, I'm not 100% sure how it's generating weights if you don't give it pre-trained weights. My thought was it's probably going to use, instead of initiating on random, it's probably going to initiate using like weights learned from COCO or ImageNet or something. So since this is a very different problem, it's not, extracting features from like RGB imagery, I definitely want to freeze them, click off of freeze model. So it'll train the whole model and not just like the end part. And then I left this selected stop when model stops improving. By default, it's going to run for up to 20 epochs if the model continues to improve. I ended up running it for 10 and found that it basically stabilized by 10, which obviously speeds up the process. So you could set that to 10 if you want, or try some different numbers in there. Okay, one thing you definitely want to make sure is that the processing type is set to GPU, and I have one GPU, its ID is 0, it's the first one. If you don't do that, it's MaskRCNN basically is not going to run on a CPU, so you need to have access to a GPU to run this. Okay, so that's that. Again, this takes a while. I'll show you the result I got. So if I go in here to analysis, history, this is trained deep learning model. So let's have a look at it here. So let's see, it only took like half an hour. Again, it'll depend on your system setup here. So you can see it did a learning rate selection on its own there. That's the learning rate range that it used. And then here's the training from 0 to 9 or 10 epochs. And you can see the progression there. And then, the lapse time and everything. All right, and then when you run those models, let me show you what you end up with. So if you go in, I'm going here to Maxwell Data again, into this folder, and this is my model out 2. This was that model run. So here you can see you get this model characteristics folder, which has some images in there. You have this model metrics HTML file, and you can open that up, and it shows you some info about the trained model. So here we see it was MaskRCNN, ResNet 50 backbone. Here's the learning rate slices. Here's the loss over epochs. Note that MaskRCNN combines several losses for the bounding box, the bounding box regression, the classification, and also the instance segmentation. So it's kind of a combined loss. Here we're not really seeing a lot of evidence of overfitting. It's actually like it's doing a pretty decent job, but it's stabilizing pretty quickly. Here's a average precision score of 0.8, and here you can see some predictions and some masks. So it looks like it might be over predicting a bit here. Okay, so note one thing here is you have multiple different collars overlapping, and that's because of the way it's broken up into chips and the way the pooling process works. You're going to end up with you can end up with multiple predictions of the same feature, and we'll look at how you can deal with that later. Okay, so anyway, that's the report there. So once you have a trained model, then you can use it to make predictions. So let's do that here. So I'm going to zoom down to a new area. Again, you generally want to assess the model on a region it hasn't seen before to see how well it generalizes, again, due to overfitting. So I'm going to turn this one off, and I'm going to turn on this one. Okay, so this is a small area in Kentucky, so similar data, but just a different extent. So let's run I'm just going to pick an extent that has a lot of features in it, and we'll try to run this model on this extent and see how it does. Okay, so to do that, we want to go into our into this image analyst toolbox again, and then into the deep learning subtoolbox, and what we're looking for is detect objects using deep learning tool. Okay, so we open that tool. It's going to ask for a raster. Again, this should be the same type of data that it was trained on. So here we're feeding it a 3-band slope shade image. So I'm going to grab that, and then it's naming the outputs. Note the output here won't be a raster. It's going to be a vector. So you're going to get some vector features. I'm going to make sure that it uses my GPU, and again, we'll leave the ID there at 0, and I'm going to set the extent to current display extent so it doesn't try to predict the entire data set. Okay, next you have to submit a model definition file, and this is something that is going to be generated by the training process. We're going to go into our model out there, and there's our EMD file. That's your model definition. So we'll grab that. Here's some arguments. Note that it has a padding defined. I left that, and that seemed to work. I set the batch size the same as it was for the training process. The threshold has to do with how confident it is about an object. So basically, it's going to return any features that have that are above 0.9 for the instance segmentation. If you wanted it to be more specific than that, we could up it. So I'm just going to change it to 0.95. Return BB boxes is whether or not you're going to have it return the instant level, pixel level vectors or the bounding box. So let's just run it for now with false, which means it's going to be the instant level. And then the tile size should be generally the same as the inputs. We're going to not do non-maximum suppression for now, so we'll just leave that off. So let's hit run here. This shouldn't take super long once it gears up and then throws the data onto the GPU. While that's running, I just wanted to mention again that if you're not sure about how this works, again, we have some material on it, but you can also look at Esri's page here. It does a really good job of explaining the components of this MaskR CNN process with links to the papers and everything. Also, the ArcGIS.learn module page steps through this pretty well too. So if you go down here to object detection models, there's MaskR CNN, and there it tells you all about it here. So it accepts some input data, a backbone, some pre-trained rates. You can run this point render thing, but we didn't do that. And there's a bunch of optional settings, and these have to do with MaskR CNN. You can see there's lots of settings there. I just use the defaults, and then you can see it. There's some other options here for fitting it and then predicting and everything. So I'd have a look at that if you're interested. Okay, so there we go. So looks like this is done for this prediction. So you can see the prediction there. Not great, but I mean it's looks like it's reasonable. I would probably need some tweaking. One thing you'll notice here is some of these features, especially the larger ones, like here, there's multiple predictions. And that's because of the way the tiling works. You're going to get multiple predictions over the same extent. Or sometimes you can get multiple predictions over the same extent. So if you do non-maximum suppression, the idea here is that it's only going to return, for overlapping features, it just returns the one with the highest confidence. Sometimes I find that doesn't work great. It just depends on the feature. So for example, this was cut in half. So if you return the most confident one, sometimes it doesn't capture the whole feature. What I found that works well for me is increasing the confidence threshold, not using non-maximum suppression, and then just merging all the features that overlap into a single feature. So here's how I would do that, kind of just with some simple geoprocessing. So I'm going to go here, I'm going to use the dissolve tool. I'm going to dissolve, and we're going to take these output features and we're just going to dissolve them. So what we should end up with now is, as you can see here, we ended up with all of them dissolved into a single feature, and all the internal overlapping boundaries are removed. Now, to get back individual features, then you could run a single part to multi-part. Oh, actually, the other way around. Run this here. So we'll grab this and output. That will work. I'm just going to let it run. Okay, so now if I open this up, let's see if it did what I thought it did. Okay, there we go. So now what it does is it breaks it up so that any contiguous area becomes a feature. So we basically took all of our features, we collapsed them into one feature by dissolving them, and we use multi-part to single part to break them into multiple features again. Based on just contiguous features, right? So anyway, that's an example of an output. for that. Note that you can run, and again, others people may disagree with how I did this. There's different rules. There's different schools of thought on how to, do some post-processing on these instance segmentation output. Okay, so a couple other things you can do with this before we go. So let's go back into our image analyst deep learning folder here. Note that if you can obtain all of the features. So these are all the original features here, and then you can actually run non-maximum suppression after the fact. So that's what this tool does. So you can again feed it features here. I'm just going to feed it the original ones, and then you can set whatever the confidence was. It should be in the table. Let's have a look here. So there's the confidence thresholds, and you can see the range from 0.95. Remember, 0.95 was our cutoff, up to 0.99. And you may want to fiddle around with that, by the way. So if you're getting like over predictions or something, you may want to set the confidence up. If you're under predicting or not grabbing all your features, you may want to set it down. It's worth playing around with. The class value field, in this case, is class. And then you can set an overlap threshold. We'll just leave it at 0. And if we run it, it'll run that non-maximum suppression operation for us. And here's what I end up with. And note, there were some issues here where it cut things off. That's why I don't always love doing this. It seems like there might be some issues with it. So that's one option. Another useful tool in here is that you can do some accuracy assessment. So there's this compute accuracy for object detection. So I have some layers here that was from the actual paper. So let's see here. These, let me make sure I have what I need here. Okay, so these features represent the hand digitized features, or the examples. And let me pull in real quick an actual data set that we got as an output from the paper here. And let me see here, vectors. Here we go. So these were the predictions from the paper. All right, so these were our predictions, and then let me see. These were our their original files. So if you wanted to run an assessment on this, then you can do that this way. So again, our detected features are the predictions. The ground features are the reference, so that would be this one. And then again, it'll create a table. We'll just leave that there. You have to give it a class field. This is the grid code for this one, and then for the ground truth, it's code. And then you can set an IOU or intersection over union threshold. We'll just leave it at 0.5. And you could set a processing mask if you only want to calculate your metrics over a certain area. So we'll just do our KY1 mask there. And if we run that, what it's going to end up producing is a table. And we can open that up here. So it gives you back for the overall, which there's only one class, so it's the same. So basically for class 1, which is our value field class, we get a precision, a recall, an F1 score, an average precision, true positives, false negatives. So you see the main issue here seems to be false negatives. So precision's 85 is pretty good. It's the recall that seems to be the issue there. And also it spits out a PDF report. So if you hover over this and click on this PDF, it should open up in your PDF reader or web browser, and it gives you some measures at different IOU thresholds. So we have one at 0.5, 0.75, and then 0.95 there. Okay, so that's an example of doing a instance segmentation. One more thing before we go. If you're interested in getting the bounding boxes as opposed to the instant segmentation, you can run just faster RCNN, which is effectively just mask RCNN without the instant segmentation component. However, you can also basically just get that from mask RCNN. So just let me show you that real quick. I'm going to go in here to Analysis, History. We'll just go back into this. And note here, if I took the return B boxes and changed that to true, then it's just going to rerun that, and now instead of getting back our instant mask, we're going to get back our rectangular bounding boxes instead. So again, it just has to do with what type of output you're interested in. You can also just run it twice and get both if you want both the pixel level mask and the bounding boxes. All right, so here, as you can see here, we ended up with bounding boxes as opposed to our instant level or pixel level masks. Again, I didn't use non-maximum suppression here, so if I wanted to do that, I could. So I'm just going to grab this output, confidence, and class, and if we run that, it should just give us back the most confident bounding box this time instead of all the overlapping bounding boxes. Okay, so I hope you found this useful. So instant segmentation, object detection using ArcGIS Pro and the mask RCNN algorithm.